What if everything you know about the beginning of time is just the second chapter of a much grander story? Close your eyes for a moment and try to picture absolute nothingness. No stars, no galaxies, not even empty space itself. Now imagine something even more baffling. A moment before time began. That's the mystery at the heart of pre-Big Bang theories, where the rules of physics as we know them dissolve into pure possibility. Scientists and philosophers have wrestled with this question for decades, not just as a thought experiment, but as a doorway to understanding the very fabric of reality. Think about how bizarre it is that our entire universe, every atom, every force, every dimension, could emerge from a single, unimaginably dense point. But here's the twist: the Big Bang might not be the true beginning. Some theories suggest our cosmos is just one link in an endless chain of universes, each born from the collapse or collision of another. Others propose a timeless realm of quantum fluctuations, where existence flickers in and out like a candle in the wind. The deeper we dig, the more the question shifts from what happened before to, does before even have meaning when time itself isn't constant? This isn't just speculation, it's a frontier where science brushes against philosophy, where the tools of mathematics meet the limits of human imagination. And that's what makes it so thrilling. Whether you're drawn to the elegance of loop quantum gravity, the holographic principle, or the mind-bending idea of a cyclic multiverse, these theories do more than rewrite textbooks. They challenge us to rethink our place in the grand scheme of things. So let's embark on this journey together, peeling back the layers of cosmic history to explore what might have lurked in the shadows before the dawn of time. By the end, you might find that the universe is stranger, more mysterious, and far more wondrous than you ever imagined. Trying to grasp the idea of before time is like a fish attempting to understand life outside water. Our very frame of reference collapses. We're wired to think in terms of cause and effect, beginnings and endings, but at the edge of the Big Bang, those categories shatter. Physicists face this paradox daily. Our equations describe how the universe evolved after its birth, but they hit a wall when we try to rewind further. It's not just that the math breaks down, it's that the concept of before loses all meaning when time hasn't yet begun ticking. Imagine holding a book where the first page is glued shut. You can analyze every word from page 2 onward, but the story's true origin remains hidden. That's the challenge with cosmic origins. Some theories, like loop quantum cosmology, suggest time might have always existed in a quantum foam, a seething, unpredictable realm where cause and effect dance in loops rather than straight lines. Others propose that our universe is a bubble in an eternal multiverse, where before simply means outside. The real puzzle isn't just scientific, it's philosophical. If time emerged with the Big Bang, asking what came before is like asking what's north of the North Pole. Our language, even our logic, might be inadequate tools for the job. Yet that's precisely why this question captivates us. It forces us to confront the limits of human understanding while hinting at truths far stranger than fiction. Even Einstein, the genius who reshaped our understanding of space and time, once wrestled with the idea of an eternal universe. In the early 20th century, before the explosive evidence for the Big Bang emerged, he proposed a radical alternative, a static, unchanging cosmos that had always existed. Picture a vast, timeless stage where stars and galaxies drift in perfect equilibrium, never expanding, never collapsing, just persisting in serene balance. This was Einstein's static universe, a solution so elegant he believed it might sidestep the need for a beginning altogether. To make his equations work, Einstein introduced something he called the cosmological constant, a kind of anti-gravity force woven into the fabric of space itself. Think of it as an invisible hand gently pushing outward, counteracting the natural pull of gravity to keep everything perfectly still. At the time, it seemed like a masterstroke. But within years, observations by astronomers like Edwin Hubble revealed something astonishing. Distant galaxies weren't static at all. They were racing away from each other as if the universe itself was stretching. The cosmos wasn't eternal and unchanging. It had a birthday and it was still growing. Einstein would later call the cosmological constant his greatest blunder, but the irony is profound. Decades after his death, scientists resurrected the idea in a wildly different form to explain the accelerating expansion of the universe. What Einstein dismissed as a mistake turned out to be a glimpse of dark energy, one of the deepest mysteries in modern physics. His static universe may have been wrong, but it left behind two crucial lessons. Even the brightest minds can be blindsided by the universe's true nature, and sometimes our mistakes contain seeds of tomorrow's breakthroughs. The story of Einstein's static universe isn't just about a failed theory. It's a reminder of how science thrives on bold ideas, even when they're proven wrong. It shows us how preconceptions can shape our vision of reality, and how the cosmos delights in defying our expectations. Most of all, it proves that the search for answers doesn't end with a single brilliant mind or a single theory. It's a collective journey where every dead end still lights the path forward. What if the Big Bang wasn't a one-time event, but just the latest heartbeat in an endless cosmic pulse? The oscillating universe hypothesis paints a breathtaking picture of existence as an infinite dance of expansion and collapse, a cycle where universes are born, live, and die, only to be reborn again. Picture a cosmic accordion. Our universe expands outward in a fiery Big Bang, eventually slows under gravity's pull, then contracts back into a singularity, a big crunch, that becomes the seed for the next universe's Big Bang. In this view, time isn't a straight line with a definitive beginning, but an unbroken loop where endings and beginnings blur into one. This idea isn't just poetic, it's grounded in the physics of Einstein's general relativity. If the density of matter in our universe is high enough, gravity could eventually reverse the expansion, dragging galaxies back together in a slow-motion collapse. Imagine all the stars and galaxies now racing apart, someday reversing course like marbles rolling back down a hill. The entire cosmos would heat up as it contracts, stars evaporating into plasma, atoms breaking apart until everything condenses into a superheated point, a rebirth waiting to happen. But here's where it gets thorny. Modern observations suggest the universe's expansion isn't slowing down at all, it's accelerating, driven by mysterious dark energy. That throws a wrench into the oscillation model, since perpetual acceleration would prevent a future big crunch. Yet some theorists propose workarounds. Maybe dark energy weakens over time, or perhaps each cycle tweaks the laws of physics slightly, creating variations in each new universe. Others suggest the Big Crunch isn't the only path. Collisions between universes in a multiverse could trigger new Big Bangs, like bubbles merging in a vast cosmic foam. The most tantalizing part, if this hypothesis were true, traces of previous universes might linger in ours. Some physicists hunt for faint patterns in the cosmic microwave background, the afterglow of the Big Bang that could carry echoes of a pre-Big Bang universe. Others speculate that black holes, those enigmatic cosmic traps, might preserve information from earlier cycles like fossils in space-time. It's a chilling thought. Our universe's past might be literally written into its fabric if only we knew how to read it. Beyond the science, the oscillating universe taps into something primal, the human fascination with cycles, from seasons to civilizations. It offers a strange comfort. Even if our universe meets a fiery end, it might not be final. But it also raises unsettling questions. Would each new universe follow identical laws, or would physics reshuffle itself, creating alien realities where gravity repels or light moves backward? Could consciousness or complexity resurface in these new worlds, or is each cycle a blank slate? The hypothesis doesn't just challenge our understanding of cosmology, It forces us to confront what eternity really means and whether existence itself could be limitless, echoing through time without beginning or end. The quantum vacuum is anything but empty. Picture a vast cosmic ocean where waves of energy rise and fall unpredictably, particles flickering in and out of existence so fast they barely leave a trace. This isn't science fiction, it's the zero-point field, a seething undercurrent of reality where nothing is actually a frenzy of potential. According to quantum physics, even in the deepest void, space crackles with temporary particles that borrow energy from the future, existing for fractions of a second before vanishing again. It's as if the universe has a hidden pulse, a restless energy that defies the very idea of stillness. Now imagine one of those fluctuations not fizzling out, but ballooning catastrophically like a single bubble in a boiling pot growing to engulf the entire stove. Some theorists propose that's exactly how our universe began, a random quantum hiccup in an otherwise featureless void, stretched beyond its moment by a runaway process called inflation. In this scenario, the Big Bang wasn't a singular explosion, but the aftereffect of a quantum event so tiny it makes an atom look gigantic. The math suggests that given enough time, or perhaps no time at all, the quantum foam could spontaneously birth entire universes, each with its own laws of physics, like soap bubbles separating from a larger film. But here's where it gets even stranger. The quantum vacuum isn't just a backdrop, it might be the ultimate cosmic recycler. Some models suggest that universes could sprout from black holes tunneling through space-time, or that our entire reality is nested inside a larger parent universe, like a Russian doll of existence. And if the vacuum's energy can fluctuate once, why not infinitely? This leads to the staggering idea of eternal inflation, where new universes bud off endlessly in an unobservable multiverse, each with its own unique physics. Our cosmos might just be one accidental masterpiece in an endless gallery of failed experiments. Yet the most mind-bending implication isn't the mechanics, it's the philosophy. If universes can emerge from pure quantum potential, then nothing might be the most creative force in existence. No divine spark, no pre-existing matter, just the raw, statistical inevitability of probability playing out across eternity. It raises haunting questions. Are we here because of an unfathomably lucky roll of the dice? Or is our universe just one inevitable outcome in a sea of infinite attempts? The quantum vacuum doesn't answer these questions, it obliterates the assumptions behind them, showing us that reality's foundations might be far weirder and more wonderful than we ever dreamed. What if the death of our universe isn't an end, but a cosmic metamorphosis, a transformation so profound it births a new reality from the ashes of the old? That's the spine-tingling premise of Roger Penrose's conformal cyclic cosmology, a theory that turns the conventional timeline of the universe inside out. Picture this, trillions of years from now, when the last black holes have evaporated and all matter has decayed into faint ripples of radiation, the universe won't just fade into darkness. Instead, in a moment of exquisite symmetry, its bleak, empty future could become the fiery dawn of another. Penrose's insight hinges on a bizarre quirk of physics. As the universe expands toward heat death, its structure stretches to a state where time and distance lose all meaning, a condition called conformal invariance. Imagine zooming in on a snowflake until its intricate details blur into perfect symmetry. At this cosmic scale, a cold, lifeless future universe and a hot, dense Big Bang become mathematically indistinguishable. In Penrose's vision, this isn't just a coincidence, it's a bridge. The infinite sprawl of one epoch's end seamlessly stitches onto the explosive beginning of the next, like a Möbius strip of reality where the final page of one story becomes the opening line of another. But how could information possibly survive such an extreme reset? Penrose proposes that gravitational waves, ripples in spacetime itself, might carry echoes of the previous universe into the next. He and his collaborators claimed to have spotted faint, circular patterns in the cosmic microwave background, nicknamed Hawking points, which they argue could be imprints of supermassive black holes from a prior cosmic cycle. Think of them as cosmic fingerprints left on the newborn universe, subtle clues that were not the first iteration of existence. Critics point out gaps in the theory, like how quantum effects might disrupt this elegant symmetry, or why only gravitational information seems to transfer between cycles. Yet, even if the details remain contentious, Penrose's framework challenges something deeper, our instinct that time is a straight line. In his model, the arrow of time isn't erased but repurposed. Each cycle begins with low entropy, not because of some initial fine-tuning, but because the end of the previous universe inherently resets the clock. It's a dizzying thought. Entropy, the force that drives aging and decay in our world, might be the very mechanism that allows universes to renew themselves. Beyond the equations, conformal cyclic cosmology touches something mythic, the ancient human longing for renewal, the phoenix rising from its own ashes. But this isn't mythology, it's a testable hypothesis. If future telescopes confirm those swirling patterns in the cosmic background, we might have tangible evidence that our universe is just one note in an infinite cosmic symphony. And that raises haunting questions. Are the constants of nature, the laws we consider fundamental, merely heirlooms passed between universes? Could civilizations in each cycle leave coded messages in space-time for their successors? Or is each rebirth a clean slate with no memory of what came before? Penrose doesn't just offer a new chapter in cosmology, he invites us to rethink what it means for existence to begin at all. What if our three-dimensional universe is just an elaborate illusion, a cosmic hologram painted onto a two-dimensional surface at the edge of reality? This isn't a plot from a sci-fi movie. It's the radical proposition of the holographic principle, a concept that emerges from the tangled mathematics of string theory and black hole physics. Picture reality like a credit card security hologram. What appears as a three-dimensional image is actually encoded on a flat, two-dimensional surface. Now scale that up to universal proportions. Every star, every planet, even your own consciousness, might be nothing more than data flickering on a distant primordial screen. The roots of this idea trace back to an unexpected place, the study of black holes. When physicists calculated how information behaves at a black hole's boundary, they stumbled upon a baffling discovery. The maximum entropy, the total information content, of any region of space isn't determined by its volume, as you'd expect, but by its surface area. It's as if the universe secretly operates like a hard drive, where all the action happens on the casing rather than inside. This revelation led to a staggering implication. Our perceived three-dimensional reality could be a projection from a two-dimensional membrane existing at the universe's farthest edge, or perhaps even from outside it altogether. Now apply this to the pre-Big Bang era. If the holographic principle holds, the singularity that birthed our cosmos might not have been a point of infinite density, but a two-dimensional surface packed with quantum information. Imagine a cosmic projector so powerful it doesn't just display images, it generates space-time itself. In this view, the Big Bang wasn't an explosion of matter but a transformation of information, where data on a primordial screen suddenly processed itself into the dimensions we now call length, width, and depth. The universe didn't emerge from nothing, it unfolded from a deeper layer of reality we're only beginning to decode, but here's where it gets even wilder. Some versions of the holographic principle suggest that time itself might be an emergent property, a byproduct of how information is processed on that hidden surface. Before the Big Bang, time as we know it wouldn't exist, just timeless, changeless data waiting to be rendered. This could explain why asking what happened before feels so paradoxical. You're essentially asking what a computer program looked like before the processor started running it. The question melts away when you realize the code and the execution are two sides of the same coin. Critics argue the holographic principle remains speculative, its mathematical elegance outstripping current experimental reach. Yet tantalizing hints linger. Physicists have found holographic descriptions can simplify notoriously complex problems, like quark-gluon plasma in particle accelerators, with eerie accuracy. And if future experiments detect anomalies in cosmic microwave background radiation, tiny fingerprints of quantum fluctuations from the universe's first moments, they might reveal whether those fluctuations originated from a two-dimensional boundary rather than three-dimensional space. Beyond the equations, the holographic principle forces us to confront a humbling possibility. Everything we experience, the feel of sunlight, the weight of a stone, the vastness of galaxies, might be the universe's grandest illusion, a shadow play cast by something infinitely stranger. It's as if we've spent centuries studying the images on a movie screen, unaware the real story lies in the projector's whirring gears. Whether this theory ultimately holds or not, it rewires our intuition about reality's true nature, suggesting that the deepest answers about existence might not lie in the stars, but in the invisible scripts from which they're written. Imagine the universe not with a bang, but with a rebound, like a cosmic rubber band stretched to its limit, then snapping back with enough energy to birth reality anew. That's the heart of loop quantum gravity's bold vision. The Big Bang wasn't a beginning from nothing, but a dramatic bounce from a previous universe's collapse. While most theories hit a wall at the singularity, a point of infinite density where physics breaks down this framework offers an escape hatch. Picture a collapsing universe not ending in destruction, but compressing until quantum effects kick in like a safety net, sending everything springing outward again in a fiery rebirth. The magic lies in the fabric of spacetime itself. Loop quantum gravity suggests spacetime isn't smooth and continuous, as Einstein presumed, but woven from tiny, indivisible threads. Think of it as a cosmic mesh where each loop carries a quantum of area or volume. When gravity becomes extreme, these loops resist further squeezing, turning the crushing weight of collapse into a repulsive force. It's like trying to compress a mattress to the size of a walnut. Eventually, the springs push back. In this model, the Big Bang singularity isn't a dead end, it's a cosmic trampoline. What's thrilling is how this reshapes the origin story. Instead of a mysterious singularity, there's a predecessor universe that contracted under its own gravity, heating up until quantum spacetime effects triggered the bounce. The laws of physics needn't vanish or reset, they simply weather a phase transition, like ice melting into water. Supporters argue this solves the singularity problem neatly. No infinities, no erased information, just a universe recycling itself. But could we ever test such a wild idea? Surprisingly, yes. If a bounce occurred, subtle imprints might linger in our universe's oldest light, the cosmic microwave background. Some models predict faint swirls or anomalies in this radiation, like cosmic bruises from the pre-bounce collapse. Others suggest gravitational waves from the bounce itself might still ripple through space-time, waiting for future observatories to catch their whisper. Even the universe's expansion rate today could carry echoes of its rebound energy, like a diver's momentum after pushing off the pool floor. Critics point out gaps like how exactly quantum gravity's math handles the bounce's chaos, or why our universe appears so uniform if it emerged from a turbulent collapse. Yet the theory's elegance is undeniable. It sidesteps the existential dread of a one-time creation, offering instead an infinite rhythm of universes, each learning from the last. There's a poetic symmetry here. Stars dying in one epoch become the hydrogen seeds of the next, laws of physics subtly evolving like genetic mutations across cosmic generations. Beyond equations, the bounce hypothesis taps into something primal, the human love of cycles, of death and renewal. It suggests that even at the scale of the cosmos, endings aren't absolute. Whether the math ultimately holds or not, loop quantum gravity's vision challenges us to rethink not just how the universe began, but what it means for reality to endure. After all, if existence can bounce back once, why not forever? String theory doesn't just rewrite the rules of physics, it turns them into a cosmic choose-your-own-adventure book. Imagine a reality where the universe's fundamental constants, the strength of gravity, the mass of electrons, even the number of dimensions aren't fixed laws but random selections from an infinite menu. That's the string theory landscape, a mind-bending framework where our Big Bang wasn't a unique event, but one bubble popping into existence in an endless, frothing multiverse. Picture a boiling pot of water with bubbles constantly forming, growing, and colliding, except each bubble is a full-fledged universe with its own distinct physics, and the pot is an eternal higher dimensional expanse called the bulk. The magic and the madness of string theory lies in its tiny vibrating strings, theoretical one-dimensional objects whose vibrations dictate everything from quarks to quasars. But here's the twist: the math allows for an astronomical number of possible vibrational patterns, each corresponding to a different set of physical laws. Some configurations might produce universes where gravity is so strong stars form and die in seconds, or where electromagnetism is too weak to forge atoms. Others could sprout dimensions we can't even perceive, curled up like microscopic origami. The landscape isn't just vast, it's a hall of mirrors where every reflection is a new cosmic experiment. Now consider eternal inflation, the engine behind this multiverse. Quantum fluctuations in the bulk could trigger endless pockets of rapid expansion, each birthing a new bubble universe. Ours, with its finely tuned laws permitting life, might be a rare fluke in a sea of hostile realities. It's like shaking a cosmic soda can. Most bubbles fizzle into oblivion, but a lucky few stabilize into something complex. This idea flips the fine-tuning problem on its head. Instead of asking why our universe's constants are so perfectly calibrated for life, we might simply be in the one bubble where the dice rolled in our favor. Critics argue the landscape is untestable, a dazzling idea imprisoned by its own flexibility. But supporters point to subtle clues. If our bubble collided with another early in cosmic history, the crash might have left scars in the cosmic microwave background, like wrinkles in a bedsheet. Others hunt for exotic particles or hidden dimensions that could serve as fingerprints of the bulk. Even the cosmological constant's perplexingly small value, the force driving the universe's accelerating expansion, finds an eerie explanation in the landscape's probability games. Beyond the physics, the landscape confronts us with existential whiplash. If every possible universe exists, does reality lose meaning? Are there infinite versions of you reading this script in parallel cosmos, some where gravity failed or time runs backward? The theory doesn't just expand our notion of space, it shatters our grip on uniqueness, suggesting that every cosmic accident, every biological miracle, might be playing out endlessly across the multiverse's infinite stages. Whether it's a master key to reality or a philosophical funhouse mirror, the string theory landscape forces one humbling conclusion: our universe might not be special, just statistically inevitable. Picture two sheets of paper floating in an empty room, drifting closer until bang, they slam together in a burst of energy. Now imagine those sheets aren't paper but entire universes, and the room is an unseen higher dimensional realm. This is the startling premise of the ekpyrotic universe scenario, where our cosmic origin story begins not with a bang, but with a collision in the shadows beyond our perception. At the heart of this theory lie brains, short for membranes, massive structures existing in dimensions beyond the three we experience daily. In brain cosmology, our universe might be a three-dimensional brain adrift in a higher dimensional bulk, like a slice of bread in an infinite loaf. And here's the twist: another brain could be hovering parallel to ours, separated by a gap smaller than an atom. When these brains eventually collide, the impact releases enough energy to ignite our Big Bang, not as a singular point, but as a fiery sheet of rebirth stretching across the fabric of spacetime. The ekpyrotic model turns conventional cosmology inside out. Instead of an expanding universe emerging from a single point, it envisions a cyclical saga where brains rhythmically attract and repel. After a collision, the brains bounce apart, each carrying the imprint of a new universe. Over eons, they drift together again, drawn by forces we can scarcely imagine, setting the stage for another cosmic reset. It's as if existence itself breathes inhaling separation, exhaling collision in an endless cosmic ballet. What makes this idea so compelling is how it tackles cosmology's thorniest problems. The near-perfect uniformity of our universe, why temperatures across the cosmos match so precisely, has long puzzled scientists. Inflation theory explains it with rapid early expansion, but the ekpyrotic scenario offers an elegant alternative. The slow, pre-collision approach of brains could have smoothed out irregularities like a rolling pin over dough. Meanwhile, the model naturally avoids the singularity problem. No infinite densities, just a transfer of energy between dimensions. Yet the real magic lies in the theory's testable predictions. If our universe emerged from a brain collision, gravitational waves from that primordial event might still ripple through spacetime. Unlike inflation's random quantum fluctuations, an ekpyrotic crash would leave distinct patterns, potential fingerprints in the cosmic microwave background. Future telescopes hunting for these swirls could tip the scales between competing origin stories. Even more tantalizing, if extra dimensions exist, particle accelerators might one day produce micro-black holes that evaporate in ways betraying their brain-bound origins. Critics highlight open questions like how brains stabilize between collisions or why they align so perfectly, but the theory's boldness is its strength. It reframes the Big Bang not as genesis but as transformation, a moment where hidden dimensions reshuffled reality's deck. And if the cycle continues, our universe's fate might be written in higher dimensional geometry. One day, our brain could meet its twin again, turning the cosmos into a phoenix with no final ashes. Beyond equations, the ekpyrotic vision humbles us. We might be living on a cosmic membrane, oblivious to parallel realities brushing against ours in dimensions we can't fathom. It suggests that existence's deepest truths aren't just stranger than we imagine, they're stranger than we can imagine, playing out on a stage where time and space are merely local effects. Whether this model ultimately holds or not, it expands our imagination of beginnings, proving that even the Big Bang might just be a footnote in a much grander chronicle of collisions. Stephen Hawking once likened the beginning of the universe to asking what's south of the South Pole, a question that sounds sensible until you realize it's built on a false assumption. His groundbreaking no-boundary proposal reshapes how we think about cosmic origins by erasing the very idea of before the Big Bang. Imagine time not as a straight line with a starting point, but as a circle where past and future loop together seamlessly. In Hawking's vision at the universe's birth, time shed its familiar arrow-like quality and behaved just like space, a dimension without direction or edge. This radical shift comes from blending Einstein's general relativity with quantum mechanics. Near the Big Bang's extreme conditions, Hawking and collaborator James Hartle calculated that space-time curves back on itself like the surface of a sphere. Picture Earth's latitude lines. As you approach the North Pole, lines of longitude, which act like timelines, converge until north loses all meaning. Similarly, at the Big Bang, time becomes just another curved dimension with no boundary, no starting wall to point at and say, "This is where existence began." The implications are staggering. Without a boundary, there's no need for a creator or a mysterious first cause. The universe simply exists, self-contained and self-explanatory. Quantum fluctuations near this smooth, four-dimensional curve could have spontaneously generated the seeds of galaxies, like bubbles forming in a pot of boiling water. Hawking's math suggests the cosmos bootstrapped itself into being, trading the problem of a beginning for the elegance of a closed geometry. Critics counter that the proposal dodges the hard question of initial conditions by redefining time itself. Yet Hawking's genius was in recognizing that our language and intuition fail at such extremes. We're wired to think in terms of cause and effect, but quantum cosmology operates by different rules, where probabilities replace certainties and nothing is a teeming vacuum of potential. His model doesn't just avoid singularities, it renders them linguistic relics, like calling Earth flat because edge feels comforting. Evidence remains elusive, but tantalizing clues linger. If the early universe's quantum jitters left specific statistical patterns in the cosmic microwave background, subtle deviations from randomness future telescopes might spot them. Some theorists even suggest that black holes, those cosmic traps where time distorts beyond recognition, could be miniature testing grounds for no-boundary physics. What makes Hawking's idea endure isn't just its mathematical beauty, it's how it reframes our existential puzzles. If time has no starting edge, then the search for before becomes as futile as hunting for the wind's birthplace. The universe isn't a story with a first page, it's a Möbius strip of causality where asking how it all began might be the wrong question altogether. Black holes aren't just cosmic vacuum cleaners, they might be the ultimate survivors, carrying fingerprints of dead universes into newborn ones. Picture a supermassive black hole from a collapsing cosmos, so dense and resilient that not even the violent rebirth of reality can erase it. According to cutting-edge theories, these primordial titans could have endured a hypothetical Big Crunch, the collapse of a previous universe, emerging intact to become the gravitational seeds for galaxies in our own cosmic epoch. It's as if the universe left breadcrumbs for itself, a way to pass on structural blueprints across cycles of destruction and creation. The math behind this idea is as elegant as it is mind-bending. When a universe contracts toward a big crunch, most matter and energy would be annihilated in the unimaginable heat and pressure. But black holes, especially the supermassive ones lurking at galactic centers, are different. Their event horizons act like cosmic armor, shielding their interiors from the crushing chaos outside. Some models suggest that as space-time fractures near the singularity, these black holes could tunnel through the wreckage, not as physical objects, but as quantum gravitational imprints emerging on the other side as perturbations in the newborn universe's energy field. These distortions wouldn't just linger, they'd serve as gravitational anchors, accelerating the formation of stars and galaxies in their vicinity. What's mesmerizing is how neatly this solves one of astronomy's biggest puzzles: why supermassive black holes appeared so early in our universe's history. Telescopes have spotted these behemoths in the distant cosmos, fully formed when the universe was less than 1 billion years old, far too quickly for conventional growth models. But if they were inherited from a prior cycle, they'd already be mature at the moment of our Big Bang, like cosmic heirlooms passed between generations. Observations of unexpectedly ancient black holes like the 700 million solar mass monster powering quasar J0329 suddenly make eerie sense if they're relics rather than newborns. The implications spiral outward. If black holes can transcend cosmic cycles, they might carry more than just mass, they could ferry information. The holographic principle suggests all data within a black hole's volume gets encoded on its surface. During a bounce, this data might not vanish but transform, imprinting itself on the fabric of the next universe like a watermark on paper. Some theorists even speculate that subtle patterns in the cosmic microwave background, those faint temperature fluctuations from the universe's infancy, could contain statistical anomalies betraying this inheritance. Future gravitational wave detectors, sensitive enough to probe the earliest moments after the Big Bang, might one day catch whispers of THESE, Chinese letter universes in the ripples of spacetime itself. Yet the most profound consequence isn't observational, it's philosophical. If black holes bridge cosmic epochs, then the universe isn't just cyclical, it's learning. Each iteration could build on the gravitational architecture of the last, evolving structures over infinite time. Stars might form more efficiently, galaxies organize more precisely, with each rebound refining the cosmic recipe. And if consciousness depends on stable structures like planets and chemistry, could this iterative process make life increasingly likely with each new cycle? The theory doesn't just reshape our past, it reimagines eternity as a cosmic apprenticeship where each universe inherits the wisdom of its ancestors, written not in stone but in the silent gravity of ancient black holes. If reality lasts long enough, could random fluctuations in the void accidentally assemble a fully formed consciousness, a lone mind blinking into existence without a body, a universe, or even a past? That's the chilling premise of the Boltzmann brain paradox, a thought experiment that turns the nature of existence inside out. Named after 19th century physicist Ludwig Boltzmann, who first grappled with how order emerges from chaos, the paradox suggests that in an eternal or infinitely large cosmos, the spontaneous formation of self-aware entities might be more likely than the orderly evolution of an entire universe like ours. Picture a vast, lifeless void where particles occasionally collide by chance. Given enough time, think trillions upon trillions of years, those random fluctuations could theoretically arrange atoms into any configuration, no matter how improbable. A single, disembodied brain with false memories of a life that never happened is statistically far simpler than constructing galaxies, planets, and civilizations. So why do we find ourselves in a lush, structured cosmos instead of floating in nothingness as momentary glitches in the dark? The paradox cuts to the heart of cosmology's biggest questions. Is our universe's apparent fine-tuning real, or just a fleeting anomaly in an endless sea of chaos? Some theorists use the Boltzmann brain dilemma to challenge eternal inflation and other models predicting infinite universes. If reality truly has no end, then over infinite time, even the most absurdly unlikely events become inevitable. You, or more accurately, a brief, hallucinatory version of you, could spontaneously materialize right now from quantum static, complete with fabricated memories of reading this script. The fact that we perceive a consistent, lawful cosmos suggests either that the universe isn't eternal in the way some theories propose, or that we're missing a crucial piece of physics that prevents such aberrations. Yet there's a twist. The paradox might actually hint at deeper truths about consciousness itself. Modern neuroscience suggests our experience of reality is already a fragile construct, a curated simulation stitched together by the brain. In that light, the Boltzmann brain isn't just a horror story. It's a mirror forcing us to ask how we distinguish real perception from illusion. If a consciousness emerging from chaos could perfectly mimic your lived experience, does the distinction even matter? Critics argue the paradox is a reductio ad absurdum, a deliberate exaggeration to expose flaws in certain cosmological models. But its persistence in debates reveals how deeply intertwined physics and philosophy are when grappling with origins. Whether a warning sign for theories of eternal existence or a profound meditation on the nature of awareness, the Boltzmann brain reminds us that in the quest to understand reality's beginnings, we might first need to define what real truly means. What if the Big Bang wasn't the universe's origin story, but the opening sequence of an unfathomably advanced simulation? This is the provocative core of the simulation hypothesis, a theory that casts our entire cosmos as a digital construct, its fundamental constants not randomly set but deliberately coded by some higher dimensional programmer. Think of the universe as perfect, fine-tuning the gravity just strong enough to form galaxies, the cosmological constant improbably balanced to allow expansion without tearing reality apart. These precise values, which physicists often chalk up to luck, might instead be evidence of intentional design, like finding a library where every book's spine aligns to millimeter precision. The idea gains traction when you consider digital physics, a framework where spacetime isn't smooth and continuous but pixelated at the tiniest scales. Imagine reality as a cosmic video game with Planck-length pixels and time ticking in discrete steps like a processor's clock cycle. In such a universe, the Big Bang could resemble a program's initialization sequence, allocating memory, loading initial conditions, and executing the first lines of cosmic code. Even quantum uncertainty, with its probabilistic flickers, fits eerily well with how a simulation might conserve computational resources, rendering details only when observed. But who or what could build such a simulation? Some theorists point to post-human civilizations, civilizations so advanced they've mastered universe-scale computation. Picture a future where our descendants harness energies beyond stellar scales to run ancestor simulations, recreating history with such fidelity that conscious beings inside believe they're real. Alternatively, the programmer might not be biological at all, but an AI that evolved in a parent universe, spinning off nested realities like a tree branching into infinity. Critics argue the hypothesis is unfalsifiable, a high-tech version of God did it. Yet supporters counter that certain observational anomalies could betray our simulated status. Glitches in high-energy particle collisions, unexpected limits in small-scale measurements, or even odd mathematical patterns in cosmic background radiation might hint at underlying code. Some even suggest that if the universe runs on finite processing power, we might eventually detect resolution limits in extreme experiments, like a video game character noticing pixelation when zooming in too far. The philosophical implications are dizzying. If we're in a simulation, does the programmer intervene or set the rules and let chaos unfold? Are black holes cosmic garbage collectors compressing data to free up memory? And most unsettling, if simulations can contain conscious beings, how many layers deep might we be? The hypothesis doesn't just challenge our cosmic origins, it redefines reality itself, suggesting that the mystery of existence might not lie in the stars, but in the ones and zeros of a universe-sized computer humming silently in the dark. Time's arrow points stubbornly forward in our everyday experience. Eggs crack but never uncrack. Coffee mixes with cream but never separates. This irreversible flow, governed by the second law of thermodynamics, hinges on one cosmic oddity. Our universe began in a state of astonishingly low entropy, as if someone carefully stacked a house of cards in a hurricane. The deeper mystery isn't just why entropy was low at the Big Bang, but why it wasn't zero. An absolute uniformity that would leave no room for complexity, stars, or life. This delicate balance suggests our cosmic origin wasn't random. Something set the stage. One radical explanation flips time's arrow on its head. Imagine a mirror universe branching backward from our Big Bang, its entropy increasing as ours decreases, like two rivers flowing in opposite directions from a single spring. In this two-headed model, proposed by physicists like Sean Carroll, what we call the Big Bang becomes a moment of symmetry, a temporal equator where two universes emerge with opposing arrows of time. From our perspective, their past is our future, and their crushing heat death becomes our improbable beginning. It's as if reality folded itself at the singularity, creating paired cosmic narratives that balance entropy like a seesaw. Another approach ties entropy to cosmic rebirth. If conformal cyclic cosmology or quantum bounces reset the clock with each new universe, entropy might not vanish but transform. Picture a sculptor recycling clay. The intricate statue of one epoch becomes the raw lump of the next. In Roger Penrose's vision, when a universe expands into infinite thinness, its particles lose all scale, making a cold, empty future indistinguishable from a hot, dense beginning. The low entropy we observe could be a relic of information preserved through this cosmic recycling, like a message passed through countless translations. Yet the most unsettling possibility is that our universe's fine-tuned starting point wasn't special at all, just a statistical fluke in an infinite multiverse. Among countless failed realities where entropy clumped into chaos, ours is the rare lottery ticket where matter arranged itself just right. This anthropic reasoning feels like a cop-out, but the math is chilling. In eternity, even the impossible becomes inevitable. Whether time's arrow points to a deeper symmetry, a cyclical reset, or pure luck, one truth emerges. Our universe's delicate beginnings hint at layers of reality we've barely glimpsed. The deeper we probe, the more the question shifts from why was entropy low to what kind of cosmic architecture could manufacture such precision. The answer might rewrite not just our past, but the nature of existence itself. Imagine the universe as a frozen lake on the brink of spring, seemingly solid but secretly unstable, one crack away from shattering into liquid chaos. That's the essence of vacuum metastability, a theory suggesting our cosmic home might exist in a precarious, false vacuum, a state that isn't the lowest possible energy level but has been trapped there since the Big Bang, like a boulder balanced on a mountainside. And if something knocked it loose, the entire fabric of reality could undergo a catastrophic phase transition, rewriting the laws of physics in an instant. But here's the twist: this existential threat might also be the key to our very existence. The idea hinges on quantum field theory's revelation that what we call empty space is anything but empty. It's a seething quantum foam where fields dictate the behavior of particles and forces. Most fields settle into their true vacuum, the lowest energy state possible. But if a field gets stuck in a false vacuum, a higher energy local minimum, it creates a universe with seemingly stable, yet fundamentally fragile physics. Picture a marble resting in a shallow dent on a slope. It'll stay put until a nudge sends it tumbling downhill. Now apply this to cosmic origins. If a parent universe existed in such a metastable state, a random quantum fluctuation could have triggered a bubble of true vacuum to nucleate within it. This bubble would expand at near light speed, its walls rewriting physics as they advance. From inside the bubble, the event would look like a Big Bang, a sudden eruption of energy birthing a new cosmos with entirely different fundamental constants. Our universe might be that bubble, its physics not finely tuned but randomly inherited from a quantum accident in a long-dead ancestor reality. The math behind this is both elegant and terrifying. Calculations suggest a false vacuum decay would propagate outward like a chain reaction, obliterating everything in its path. The new physics inside the bubble could be unrecognizable. Gravity might repel, light could crawl, atoms might never form. Yet statistically, given infinite time or space, some bubbles would inevitably stabilize into hospitable universes like ours. It's like a cosmic version of natural selection. Most decay events spawn sterile voids, but a rare few hit the jackpot, producing conditions ripe for complexity. Evidence for this theory is speculative but tantalizing. If our universe emerged from such an event, residual gravitational waves from the bubble's violent expansion might linger in the cosmic microwave background, subtle swirls waiting for next-generation telescopes to detect them. Even the universe's startling uniformity could be a clue. A vacuum decay would have reset everything with surgical precision, erasing any wrinkles from the parent cosmos. Beyond the physics, the implications are staggering. A vacuum decay could happen again, not just in some distant corner of space, but everywhere simultaneously, erasing reality without warning. But it also offers a humbling perspective. The laws we consider absolute might just be local ordinances, temporary rules in a single bubble floating in an infinite foam of possibility. Whether this theory holds or not, it forces us to confront the fragility of existence and the awe-inspiring chance that we're here at all. What if numbers aren't just tools we invented to describe reality? What if they are reality? That's the radical heart of Max Tegmark's mathematical universe hypothesis, a theory so audacious it redefines existence itself. Imagine peeling back the layers of the cosmos like an onion, past atoms, past quantum fields, until you reach the final layer, pure abstract mathematics. No matter, no energy, just equations waiting to be instantiated. In this view, our universe isn't governed by math, it is math, a specific structure that woke up when the Big Bang pressed play. Tegmark's framework treats the cosmos like a geometric shape in an infinite library of possible shapes. Think of a triangle. Its essence exists independently of whether anyone draws it. Similarly, the mathematical structure describing our universe, with its 4 dimensions, quantum wave functions, and cosmological constants, exists eternally in a Platonic realm of possibilities. The Big Bang, then, wasn't the creation of something new, but the activation of a pre-existing equation. It's as if reality is a DVD, and the moment of cosmic ignition was simply the player starting the disc. The content was always there, latent in the code. This idea elegantly sidesteps the nagging question of why math describes the universe so uncannily well. From the spirals of galaxies to the orbits of electrons, nature dances to numerical rhythms. If math isn't just a language we use but the fundamental substrate of existence, its precision isn't a mystery, it's inevitable. Even the apparent fine-tuning of physical constants loses its strangeness. Different mathematical structures would manifest different laws, and we simply inhabit one where the numbers allow for complexity. Critics argue this blurs the line between map and territory. Does positing math as reality explain anything, or just push the mystery deeper? Yet Tegmark counters with a thought experiment. If an advanced alien civilization developed physics, would their equations resemble ours? If math is universal, the answer must be yes. The same Pythagorean theorem would hold on Alpha Centauri, not because we share a cultural invention, but because it's woven into the fabric they're measuring. The implications spiral into the surreal. If every mathematically possible structure exists somewhere, then universes with different dimensions, forces, or even wholly alien logics must exist in parallel. Our cosmos, with its quarks and quasars, is just one page in an infinite textbook of self-consistent mathematical systems. Some might be too unstable for life, others too simple for complexity, but their existence isn't contingent on our observation. They just are, like prime numbers or fractals, timeless and unobserved. Where the theory truly dazzles is in its resolution of the multiverse debate. Unlike string theory's landscape or inflationary bubbles, Tegmark's mathematical multiverse requires no extra dimensions or untestable physics. It simply states that all coherent mathematical structures are equally real, rendering our universe no more privileged than a single solution to an equation among countless others. The anthropic principle, the idea that we observe this particular universe because it's compatible with our existence, finds its purest expression here. We're not selecting one universe from many, we're a subset of a structure that permits self-aware observers. Could we ever test such an abstract idea? Tegmark suggests looking for unreasonable mathematical elegance in fundamental laws patterns so precise they hint at deeper symmetries. Others propose that if the universe's information content is finite, it might resemble a discrete mathematical object at its core. Even quantum indeterminacy fits neatly. The probabilities governing particles could reflect an underlying mathematical probability distribution. Beyond the equations, the mathematical universe hypothesis forces a Copernican-level humility. Just as Earth isn't the center of the solar system, our universe might not be the center of reality, just one instance of an eternal truth. It's a vision where Pythagoras and Planck share common ground, where the ultimate nature of existence isn't material or spiritual, but numerical. Whether the theory holds or not, it dares us to consider that the universe might not follow rules. It is the rules playing out in an endless, silent symphony of logic. What if our universe didn't start with a bang, but with a cosmic spitball? That's the bizarre yet electrifying premise of the white hole ejection theory, which flips black hole physics on its head to rewrite cosmic origins. Picture a black hole in some distant parent universe, relentlessly devouring matter and energy beyond its event horizon. Now hit rewind. According to general relativity's strict symmetry, that black hole's time-reversed counterpart, a white hole, wouldn't suck everything in but violently expel it in an unstoppable geyser of spacetime. Now imagine that eruption was so cataclysmic it birthed an entire new cosmos, our universe. This isn't just poetic analogy, the math checks out. Einstein's equations describe white holes as mathematically valid solutions, like black holes running backward in time. Matter that vanishes beyond a black hole's event horizon in one universe could re-emerge from a white hole's singularity in another, like water surging through a wormhole funnel. In this view, the Big Bang's incomprehensible energy wasn't conjured from nothing. It was the pent-up contents of a collapsed star or galaxy from a pre-existing reality, finally released after eons of compression. Imagine squeezing a tube of toothpaste until the cap pops off with explosive force. The white hole model suggests our universe might be the paste. What makes this hypothesis radical isn't just the cosmic recycling, it's how neatly it solves two perplexing riddles. First, the universe's staggering uniformity. The cosmic microwave background shows near-identical temperatures across billions of light years, as if everything was once crammed into a tiny, ultra-mixed space. A white hole's violent ejection could have blasted matter into such a homogenized state. Second, the singularity problem. Physics breaks down at the Big Bang's infinite density, but a white hole's singularity might inherit structure from its parent black hole, like a seed carrying genetic code. The universe wouldn't start from true chaos, but from a carefully compressed imprint of another reality's death. Yet the theory isn't without wrinkles. Observational evidence remains sparse, though indirect clues tantalize. Some physicists hunt for anomalous patterns in the cosmic microwave background, circular imprints that could mark a white hole's eruptive birth. Others speculate that dark matter's enigmatic presence might be debris from the parent universe, lingering like cosmic sawdust after the white hole's demolition. Even the universe's unexpected acceleration could fit. If the white hole's ejection included repulsive forces akin to dark energy, it might explain why expansion isn't slowing down. Beyond the equations, the white hole model forces us to confront a humbling possibility. Universes might not live in isolation, but in vast chains of cause and effect. Every black hole's collapse in one cosmos could sow the seeds for another's birth, threading reality into an endless tapestry of creation and destruction. It's as if existence itself follows a cosmic version of the water cycle, evaporating into singularities, condensing into white holes, and raining down new beginnings. Whether this theory ultimately holds or not, it reshapes the search for origins from a question of creation to one of transformation, where even the darkest cosmic endings might light the way to dazzling new dawns. Think of cosmic inflation not as the beginning, but as a middle chapter, an explosive expansion sandwiched between an unfathomable past and an uncertain future. The theory that our universe ballooned from a quantum speck to cosmic vastness in fractions of a second solves many puzzles, but it raises a deeper question: what set inflation in motion? Some versions of the theory point to a meta-universe, an eternal backdrop where inflationary bubbles sprout endlessly like mushrooms after rain, each one a potential Big Bang for a new cosmos. At the heart of this idea lies eternal inflation, a runaway process where space itself expands exponentially faster than light in certain regions. Picture a pot of water on a rolling boil, with bubbles forming, rising, and popping. Now imagine that boiling happens across infinite space, with some bubbles growing so rapidly they never pop. these become self-contained universes, their edges racing outward faster than any signal could cross them, isolating them forever from their parent cosmos. Our universe might be one such bubble, its Big Bang merely the moment our pocket of space-time broke free from the inflationary froth. What's startling is how this reshapes the timeline of existence. Inflation's driving force, a hypothetical field called the inflaton, wouldn't need a singular start. Instead, quantum fluctuations in the meta-universe could randomly kick regions of space into high-energy states, triggering eternal inflation. It's like tossing lit matches into a dry forest. Most fizzle out, but a few ignite wildfires that spread uncontrollably. In this view, our universe isn't special. It's just one accident in an endless chain reaction of cosmic births. The implications are staggering. If eternal inflation is real, the laws of physics in each bubble universe could vary wildly, determined by random chance as the inflaton field settles into different energy states. Some bubbles might crystallize into realities where gravity is 1,000 times stronger, or where atoms never form. We find ourselves in a hospitable one not because the meta-universe favors life, but because only in such bubbles could observers like us exist to ask the question, a dizzying example of the anthropic principle at work. Critics argue this makes the theory untestable, a kitchen sink explanation that swallows its own uncertainties, yet supporters point to subtle fingerprints. If our bubble universe collided with another during early inflation, the crash could have left bruises in the cosmic microwave background, odd temperature variations or swirling patterns that next-generation telescopes might detect. Even the universe's large-scale structure, the web of galaxies stretching across billions of light-years, could bear scars from its violent nucleation. Beyond the physics, eternal inflation forces a Copernican-scale humility. Just as Earth isn't the center of the solar system, our universe might be a backwater in an infinite metacosmos, one bubble among countless others. The true beginning recedes into the unfathomable past, leaving us with a cosmic tapestry where creation isn't an event, but a process where every moment, somewhere in the meta-universe, another Big Bang flickers to life, unseen and unconnected to our own. Whether this vision holds or collapses under scrutiny, it reminds us that reality's origins might be stranger than any singular explosion could suggest. What if black holes aren't cosmic dead ends, but cosmic wombs birthing new universes with slightly tweaked laws of physics each time? That's the spine-tingling premise of physicist Lee Smolens's cosmological natural selection, a theory that reshapes the origin story of our universe into something resembling biological evolution. Picture a black hole collapsing in a parent universe, its singularity not vanishing into oblivion, but pinching off into a new space-time bubble with its own Big Bang. In this view, our cosmos might be one of countless cosmic offspring, its fundamental constants not random, but refined across generations like a species adapting to its environment. Smolens's radical idea hinges on black holes acting as evolutionary pressure points. Every time a universe spawns a black hole, the resulting offspring universe inherits its parent's physical laws, but with tiny, random variations like genetic mutations. Universes that produce more black holes, say, by having stars that collapse efficiently, would leave more descendants, while those with inhospitable physics would fade into cosmic oblivion. Over eons, this process would favor universes fine-tuned for black hole production, explaining why ours seems so adept at making them. It's as if the cosmos has been playing a game of trial and error with black holes as the scorecard. The implications are staggering. Constants like the strength of gravity or the mass of protons might not be arbitrary, but optimized over cosmic generations for black hole fertility. Even the vacuum energy density, the force behind the universe's accelerating expansion, could be tuned to balance star formation and black hole creation. This offers a jaw-dropping alternative to the anthropic principle. Instead of asking why our universe is hospitable to life, we'd ask why it's hospitable to black holes. Life in this scenario might just be a curious byproduct of a deeper cosmic reproductive strategy. But could we ever test such a wild idea? Smolin suggests looking for fingerprints of ancestral universes in our own. If black hole singularities truly seed new cosmoses, the extreme conditions at their cores might imprint subtle asymmetries or anomalies in the distribution of matter we see today. Some physicists hunt for these clues in the cosmic microwave background's faint irregularities, while others speculate that certain particle physics paradoxes like the unexpected lightness of the Higgs boson might reflect evolutionary tweaks across universe generations. Even the mysterious lack of magnetic monopoles could hint at a lineage of universes pruning inefficiencies from their physics. Critics argue the theory is tautological. If universes evolved to maximize black holes, why doesn't ours have more of them? Others point out that without a mechanism for information transfer between universes, the inheritance of physical laws remains speculative. Yet Smolin's framework electrifies the debate by injecting Darwinian logic into cosmology, suggesting that the laws we treat as eternal might be more like local dialects in a sprawling cosmic language. Beyond the equations, cosmological natural selection forces a profound perspective shift. If true, we're not just inhabitants of a universe, we're witnesses to a much grander process where black holes are the architects of reality's diversity. It paints existence not as a one-time event, but as a branching tree of possibilities, with our universe perched on a limb shaped by eons of trial, error, and unimaginable celestial replication. Whether the theory ultimately holds or not, it dares us to see black holes not as endpoints, but as beginnings, the cosmic equivalent of seeds carried on the wind, each carrying the blueprint for a whole new world. Gravity might not be a fundamental force at all, but a side effect of the universe's hidden information structure, like how temperature emerges from countless molecular collisions. That's the radical proposition of Eric Verland's entropic gravity, a theory that reimagines gravity as an emergent phenomenon, a kind of cosmic illusion born from the way information organizes itself at the deepest levels of reality. Now take this idea back to the pre-Big Bang era, where the usual rules of physics dissolve into uncertainty. If gravity isn't primal but derivative, what does that mean for the origin of space-time itself? Verland's framework suggests that what we perceive as gravity, the curvature of space-time that guides planets and bends light, is actually a holographic projection of microscopic quantum data. Picture the universe as a vast network of entangled bits, where gravity isn't a force transmitted through space but a statistical tendency, like the way a crowd's movement emerges from individual choices. In this view, the Big Bang wouldn't have been the moment gravity turned on, but the moment the underlying information matrix reached a critical threshold, crystallizing into the familiar structures of space and time. Apply this to pre-Big Bang scenarios and the implications get dizzying. If gravity emerges from information, then before the universe cooled enough for space-time to solidify, reality might have existed in a kind of proto-state, a sea of raw data without fixed dimensions or forces. The transition to our ordered cosmos wouldn't require a singularity or divine spark, but a phase change like water freezing into ice. Some models even suggest that the universe's accelerating expansion could be a relic of this process, as the information fabric continues to reconfigure itself at scales we can't yet perceive. Critics argue entropic gravity struggles to explain certain cosmic observations, like galaxy rotation curves, without invoking dark matter. Yet supporters counter that the theory's true power lies in its unifying potential. By treating gravity as emergent, it bridges quantum mechanics and general relativity without requiring extra dimensions or undiscovered particles. If verified, it wouldn't just rewrite cosmology, it would redefine what we consider real, suggesting that the universe's deepest layers aren't matter or energy, but the invisible algorithms from which they arise. This perspective also breathes new life into holographic pre-Big Bang theories. If our three-dimensional reality is a projection from a two-dimensional boundary, as the holographic principle suggests, then gravity's emergence could be the universe bootstrapping itself into existence, translating abstract data into tangible physics. It's as if the cosmos is a self-solving equation where the answer spacetime stars us manifests from the sheer inevitability of its own logic. Whether entropic gravity ultimately holds or not, it forces us to confront a humbling possibility. The forces we thought governed reality might just be shadows on the cave wall, cast by a deeper, stranger truth we're only beginning to glimpse. Long before telescopes or quantum equations, humans grappled with the void through myth and metaphor. Ancient Egyptian creation narratives described none a primordial ocean of nothingness that existed before light or land, a formless abyss that somehow birthed the first mound of existence. The Greeks told of chaos not as disorder but as the infinite gap before order from which Gaia and Eros emerged. These stories share a striking intuition that nothingness isn't truly empty but pregnant with potential, a canvas waiting for the first brushstroke. Jump ahead 2,000 years, and Western philosophy sharpened this intuition into razor-edged paradoxes. Parmenides argued that true nothingness was logically impossible. To speak of nothing is still to make it a kind of something. His contemporary Leucippus countered with atomism, proposing that void was as real as matter, the negative space allowing movement and change. This tension echoes through medieval theology, where theologians like Augustine wrestled with creation ex nihilo, how a benevolent God could conjure reality from absolute nothing. Their solution, divine nothingness, wasn't a vacuum but a metaphysical blank slate. A null space brimming with God's will, like a silent orchestra before the conductor's first downbeat. Eastern traditions approach the puzzle differently. Taoism's Wu and Buddhism's Sunyata framed nothingness not as absence but as interdependent openness, the ground from which all forms arise and return like waves on an ocean. In the Upanishads, the pre-creation void hums with latent energy, captured in the paradoxical phrase, neti neti, not this, not that, a reminder that reality's source defies categorization. These philosophies hint at a revolutionary idea. Nothingness might be the most creative force of all, the silent partner to existence rather than its opposite. Modern existentialism flipped the script entirely. For Sartre and Heidegger, nothingness became active, a disruptive force in human consciousness. Sartre's Being and Nothingness describes how the void allows free will, our ability to negate the present, saying, "This is not enough," is what drives change. Heidegger's Das Nichts, the nothing, isn't inert but a dynamic presence that makes being perceptible, like darkness revealing stars. Here, the cosmic question becomes personal. If nothingness shapes universes, does it also shape our choices? Even contemporary physics borrows from these threads. Quantum field theory's vacuum fluctuations mirror Taoist Wu empty space teeming with virtual particles. The holographic principle's two-dimensional boundary echoes ancient creation myths where form emerges from formlessness. The most radical take comes from existential physicists like Wheeler, who suggested observers might collapse quantum potentials into reality, blending Sartre's negation with wave function collapse. What unites these perspectives is the sense that nothingness isn't an end, it's a beginning in disguise. Whether framed as divine will, quantum foam, or the space between thoughts, the void persists as both mystery and muse, challenging us to rethink not just how existence began, but what it means to be at all. Testing the before the Big Bang isn't just scientifically tough, it's like trying to recover a deleted file from a shattered hard drive. The very laws that let us investigate reality today didn't exist in the pre-bang chaos, leaving us with fragments rather than a clear trail. Yet physicists aren't entirely empty-handed. the cosmic microwave background, that faint afterglow from the universe's infancy, might hold ghostly fingerprints from events preceding our cosmic dawn. Picture the CMB as the universe's baby photo, a snapshot from when atoms first formed, freezing irregularities from earlier quantum fluctuations. Some models, like loop quantum cosmology, predict these fluctuations could carry imprints of a pre-bang collapse. Tiny anomalies, unexpected swirls, or concentric circles in the CMB's temperature patterns might betray a bounce from a prior universe. Roger Penrose's controversial claim of spotting these Hawking points in satellite data remains hotly debated, but the hunt for such relics drives next-gen telescopes like the Simons Observatory and Lightbird. Even a single verified irregularity could rewrite cosmic history. Quantum gravity experiments offer another backdoor. If space-time is fundamentally granular, as theories like loop quantum gravity suggest, high-energy particle collisions might reveal its pixelated texture. CERN's Large Hadron Collider, while not designed for cosmology, could accidentally uncover exotic particles or energy signatures hinting at extra dimensions, potential shrapnel from a pre-bang event. Meanwhile, tabletop experiments with supercooled atoms or laser interferometers probe whether gravity behaves differently at microscopic scales, a telltale sign of deeper structure beneath spacetime's smooth facade. The real roadblock isn't just technological, it's existential. Without a theory unifying quantum mechanics and gravity, we're stuck interpreting whispers through a keyhole. Did that CMB swirl come from a colliding brain, or is it statistical noise? Is a particle's odd behavior evidence of higher dimensions or just incomplete models? Until we crack quantum gravity's code, pre-bang theories remain tantalizingly just beyond empirical reach. Yet this uncertainty itself is revealing. The struggle to test these ideas forces us to confront how deeply our intuition is wired to post-bang physics, like flatlanders trying to imagine a cube. Every dead end underscores how radically different reality's foundations might be. What keeps scientists pushing forward is the possibility that even a failed experiment could illuminate the darkness. When the James Webb Space Telescope spotted inexplicably ancient galaxies, it didn't just challenge cosmic timelines, it hinted that our understanding of initial conditions might be fundamentally flawed. Similarly, future gravitational wave detectors like LISA or pulsar timing arrays could uncover primordial ripples from events so early they blur the line between before and after. The irony is delicious. To glimpse the pre-bang universe, we might need to accept that evidence could look nothing like what our post-bang physics predicts. After all, if time itself was born in the Big Bang, its precursors might obey rules stranger than fiction rules we'll only uncover by letting the universe defy our expectations. The search for answers beyond the Big Bang is pushing science into uncharted territory, not just conceptually but technologically. Imagine trying to reconstruct a crime scene where the laws of physics themselves were still forming, where time hadn't yet solidified into the steady arrow we know. That's the challenge facing researchers today, and their tools are becoming as avant-garde as the theories they test. At the forefront are quantum cosmology simulations, digital laboratories where scientists recreate the universe's first trillionth of a second using equations that bend spacetime like virtual origami. Projects like Europe's QSIM-FP consortium are harnessing quantum computers to model conditions so extreme they make black holes look tame. These aren't just abstract exercises. They're probing whether spacetime could have emerged from a quantum network, with every pixel of reality linked in a vast cosmic circuit board. Meanwhile, next-generation telescopes are turning the night sky into a time machine. The upcoming Vera-C, Rubin Observatory's legacy survey of space and time, will map billions of galaxies, hunting for anomalies in their distribution that might betray pre-bang collisions or cyclic universe imprints. Even more revolutionary is NASA's SPHEREX mission, launching in 2025. which will scan the cosmos for infrared fingerprints of quantum fluctuations from the universe's infancy, fluctuations that could carry echoes of whatever came before. And then there's the Einstein telescope, a future gravitational wave detector buried underground to sense ripples from the cosmos's first microseconds. Unlike LIGO, which listens for black hole mergers, this ultra-sensitive instrument might catch whispers of primordial phase transitions, cosmic burps from when the laws of physics crystallized out of chaos. But perhaps the wildest experiments are those that blur the line between astrophysics and quantum mechanics. In labs from Chicago to Munich, physicists are cooling atoms to near absolute zero, creating Bose-Einstein condensates where quantum effects dominate at macroscopic scales. These ultra-cold clouds behave like miniature universes, allowing researchers to simulate how space-time might emerge from quantum entanglement. Other teams are manipulating metamaterials, artificial structures with bizarre light-bending properties, to mimic hypothetical pre-bang geometries where time behaves more like space. It's as if we're building cosmic-scale models in tabletop experiments, testing whether the universe could have bootstrapped itself into existence from pure mathematics. The real breakthrough might come from an unexpected synergy between these approaches. Data from the James Webb Space Telescope's deep field images could reveal statistical patterns matching quantum cosmology simulations, while lab experiments with entangled particles might uncover hidden symmetries pointing to higher dimensional origins. Some theorists even speculate that dark matter, which outweighs visible matter 5-to-1, could be residue from a pre-bang phase, a cosmic fossil waiting to tell its story. Every null result, every failed hypothesis is still progress. Ruling out wrong paths is how science inches toward truth. What makes this era unprecedented isn't just the technology, it's the willingness to ask questions that once seemed heretical. When the Event Horizon Telescope captured the first black hole image, it didn't just confirm Einstein's predictions. It opened a window into extreme gravity regimes where time distorts beyond recognition. Similarly, future experiments might stumble upon phenomena that force us to rewrite cosmic history altogether. The ultimate goal isn't just to glimpse what preceded the Big Bang, but to understand whether before is even the right framework, or if we need a whole new vocabulary to describe existence's true scaffolding. Until then, every anomaly, every unexpected data point is a potential clue in the greatest detective story of all. How something as vast and intricate as reality could emerge from whatever came before nothing. After this cosmic journey through black holes birthing universes, brains colliding in hidden dimensions, and quantum vacuums trembling with potential, one truth emerges: the question of what came before the Big Bang isn't just about origins. It's a mirror reflecting the outermost edges of human imagination. Whether you're drawn to the elegance of loop quantum cosmology's cosmic bounce, the holographic principle's illusion of depth, or the haunting possibility that we're floating in a simulation's code, these theories share something profound. They force us to confront how little we truly grasp about reality's scaffolding. Consider the sheer audacity of these ideas: entire universes springing from black holes like cosmic seeds, time itself dissolving into a shapeless void before the bang, or mathematical structures waiting timelessly to be instantiated. Each theory is a testament to humanity's refusal to accept "we don't know" as a final answer. Yet for all their brilliance, they also highlight a humbling paradox. The tools we use to investigate reality, math, physics, even language, might be fundamentally unequipped to describe what lies beyond spacetime's birth. It's like trying to decode a symphony with only a thermometer. That's where you come in. The most thrilling part of this mystery isn't just the answers we've proposed, it's the questions still lurking in the dark. Maybe Penrose's conformal cycles resonate with you, or Smolin's evolutionary universes feel more compelling. Perhaps you're convinced we're missing something even wilder, something no one's dared to theorize yet. After all, every groundbreaking idea once sounded like science fiction until evidence proved otherwise. So hit pause and let this simmer. If the universe could emerge from a quantum fluctuation, a colliding brain, or a mathematical truth, what does that say about the nature of existence itself? And if time is just an emergent property, could before be a linguistic phantom, a question as nonsensical as asking what's north of the North Pole? The comment section isn't just for reactions, it's a lab for collective curiosity. Drop your boldest theories, your lingering doubts, or even your favorite cosmic metaphors. Because the next big breakthrough might not come from a telescope or a super collider, but from someone watching this video, staring at the night sky, and wondering what if we've had it backward all along. One thing's certain, the universe owes us no answers, but the fact that we keep asking, that's what makes this story so extraordinary. Whether we're holograms, cosmic rebounders, or statistical flukes in an infinite multiverse, the search itself is what elevates us from stardust to storytellers of the grandest tale there is. So keep questioning, stay unsatisfied, and remember, the most exciting chapters of this mystery might still be unwritten.